Hello, y'all. Welcome to lesson 98 of my DP chemistry curriculum. Today we're going over reactivity 3.1.7. We're going to talk about how acids react with bases and neutralization reactions. Formulate equations for the reactions between acids and metal oxides, metal hydroxides, hydrogen carbonates, carbonates, and we'll also cover ammonia and amines. So, with that said, let's talk about this first word we use. So, when we have an acid plus a base, we call this a neutralization reaction. Neutralization reaction. And this is because when we look at our pH scale, we have alkali by the 14 area, acidic by the 0, and right in the middle we have neutral. And so when we add these together, we actually shift the pH back towards neutral. Something with acid will be shifted more towards alkali. Something alkali will be shifted more towards the acid, eventually coming around to pH 7 or neutral. Once again, those three reactions that we're going to do are metal oxides and hydroxides. We're also going to do hydrogen carbonates, and carbonates. And we're going to conclude with ammonia and amines. And these will be for both strong acids and weak acids. It doesn't really matter when we're talking about an acid-base reaction. We're more talking about that proton transfer of the hydrogen. Some key terminology to have before we really jump in is generally when we're talking about insoluble bases, soluble, meaning bases that don't dissolve, we generally just refer to these as bases. So anything that doesn't dissolve we'll generally refer to as a base. Anything that is a soluble base, we actually refer to as alkali. Alkali. And those will turn the solution alkaline. So they will make it more basic. So that's the terminology we'll be using throughout. And without further ado, let's actually look at these reactions. So starting with the first one, metal oxides. So for metal oxides, I'm going to use the term MO, M for metal, O for oxide. And like we mentioned earlier, this is an acid plus a base, so this will be neutralization. When we do this, the two main things are the metal cation, so M plus, will bond with the acid anion. Now, in all of these, we're going to refer to our acids as HA. That will be our acid. And so it will bond with the acid anion, A minus, and that will produce what we call an ionic salt. So that's the first part of the reaction, and that will have the formula Ma. The metal cation plus the acid anion will form Ma. Now, on the other hand, we still have the hydrogen, so the hydrogen ion, H plus, bonds with oxide ion, O2 minus, and when it bonds with that oxide ion in a 2-to-1 ratio, we get H2O. So we're going to produce an ionic salt and water. We can look at the general formula as our M bonded to our O plus our H bonded to our A reacts to produce Ma plus H2O. We can see a real example, and I'll try and do all these real examples in a consistent color. So if we look at the reaction of copper oxide, CuO, which would be a solid base, plus 2HCl already in solution, so we're going to assume aqueous. Those will react to form CuCl2. This will now be aqueous, plus H2O liquid. And so that's a example of our metal oxide reaction. Similarly to metal oxides, we also have our metal hydroxide reactions. And this is pretty much the exact same thing, except now we have MOH for metal plus hydroxide. And it's going to be very similar. Our metal cation reacts, or I guess better to say bonds with our acid anion to produce Ma again. So we still get the same ionic salt. Oops, ionic salt. But now the difference is our hydrogen bonds with hydroxide. And once again, we're still going to produce water, H2O. So we can go ahead and see this in action. MOH plus H bonded to A will react to produce Ma once again plus H2O. And if we want to see a real example of this, we can look at the reaction of maybe sodium hydroxide, NaOH, and let's say this is already our solution, aqueous. We combine that with nitric acid, HNO3, also aqueous. And in this reaction, we will once again produce our metal salt, NaNO3, sodium nitrate, and that will also be aqueous plus H2O liquid. So you'll notice metal hydroxides and metal oxides are pretty similar. They react almost exactly the same. The only difference is we're going to have a different ratio because our acid needs 2 hydrogen for every 1 oxygen versus 1 hydrogen for every 1 hydroxide. All right, so that is hydroxides and oxides. So now we'll look at carbonates and first, and then we'll do hydrogen carbonate. So we're still looking at metal carbonates. So in this example, our metal carbonate is going to be MCO3, as CO3 is the carbonate ion, and M will still represent our metal. Now, in this reaction, very much like in our other ones, the metal cation bonds to acid anion, A minus, and we will still produce an ionic salt, which will represent by Ma. So it's still pretty similar as before. The metal is still going to form this ionic salt regardless, but here's where it becomes a little different. The hydrogen ion will react or bond with carbonate, CO3 2 minus, to produce two things. CO2, gas, and water. So now that hydrogen is going to react with carbonate, and the hydrogen is going to strip one of the oxygens off to make our water, leaving the remaining CO2 as gas that leaves the solution. We can see an example, the general MCO3 as our metal carbonate, plus our HA, and we'll get Ma plus H2O plus CO2. A real life example of this might be magnesium carbonate. We'll start it the same way. Magnesium carbonate, MgCO3. This is going to be a solid base plus 2 hydrochloric acids in solution. That will react to form magnesium chloride plus CO2, aqueous CO2 gas plus H2O liquid. Now, one of these things, the CO2 gas, is usually easy to see. You can see the production by, you can see some gas bubbles rising. But there's other ways to make sure that this is CO2 being produced and not some other gas, like maybe hydrogen gas, which can be the product between an acid and a solid metal. So the way we can generally check for the presence of this, and I'll choose a different color, but we can check for presence of carbon dioxide by bubbling through lime water. When we put it through lime water, which uh, is just a mixture of calcium hydroxide, this will produce calcium carbonate, CaCO3. The thing about calcium carbonate is this is a solid precipitate, and solution turns white. So as we put that CO2 gas through our calcium hydroxide, we produce the solid CaCO3, which is white in solution, and you can see the lime water change from a clear solution to a milky white color, and that confirms the presence of carbon dioxide. All right, moving on to metal hydrogen carbonates. Hydrogen carbonates, which is MHCO3, or metal bicarbonates, once again, are metal bonds with a minus, so our cation bonds with our anion. And of course, here our hydrogen reacts with HCO3 minus to produce. Once again, we are going to have CO2 plus H2O. Very much like the hydroxide versus the oxide, we just need one less hydrogen because that hydrogen is already present in our hydrogen carbonate. So one of the most common reactions we see of this, and we'll do the very brief version first, plus HA reacts form Ma plus CO2 plus H2O. The most common form of this reaction that you've probably all seen before is baking soda with vinegar. So NaHCO3, so sodium bicarbonate, this is baking soda, plus our vinegar, CH3COOH. Those will react to form sodium acetate, NaCH3COO plus H2O plus CO2. Gas, liquid, aqueous, solid. So this is one of the most common reactions you'll ever see with metal hydrogen carbonate. It's baking soda plus vinegar. A very simple reaction used to make volcanoes erupt if they're paper mache in a science fair, but a fun one nonetheless. All right, the last group of reactions is ammonias and amines. So with ammonias and amine, now ammonia is NH3, and an amine is going to be some type of R group, some type of long chain of hydrocarbons, NH2. So when we have this reaction, these are still going to be neutralization. However, these just produce a salt. The fact is, nitrogen contains a lone pair of electrons. So when we look at nitrogen in ammonia or in our R group, it has this lone pair of electrons right here at the top. And these are the ones we're referring to. These are capable of accepting a hydrogen ion to produce ammonium, NH4 plus. Ammonium. So this is acting as a base because it is accepting the H plus. Following the Lewis definition of a base, it is an electron pair donor. So the thing is, that NH4 plus is a cation and attracts the acid anion to produce a salt. So this is still going to produce ionically bonded salt. It's just different than the metal hydroxides because this is not a metal salt. This is salt based with ammonium as our cation, and they will electrostatically attract the acid anion. So we can look at this reaction as NH3 plus HA will produce NH4 plus, and that is what we're going to be using to represent our ion, electrostatically bonded to A minus. And so those are going to form this ionic bond. Now, a real version of this reaction might be ammonia, NH3 gas, plus vinegar, CH3, COOH, and that would be aqueous. And we're going to produce ammonium acetate, NH4CH3COO. So basically that hydrogen is going to make that transfer over to ammonia, becoming ammonium, and then that's going to electrostatically bond to our remaining anion. How does this change for our amine? Well, if we look at our amine, such as CH3, NH2, so methanamine, and we react that with nitric acid, HNO3, it doesn't actually change all that much. This H is going to go ahead and be attracted to the ammonia. It's going to turn that into ammonium, still bonded to the hydrocarbon group. And we're going to have CH3, NH3, and that'll be positive, which then attracts the nitrate, NO3. And so we're going to end up with this salt between the electrostatic attraction of our ammonium and our acid anion. So hopefully this helps you learn a little bit about the reactions that these acids take with these various bases, and have a great day.